Can you hear me well? Type 1 in the chat if you can hear me well. Oh, lovely, lovely. So happy New Year, and Merry Christmas, if you haven't seen me before. So today will be part physics, part maths. So the problems will be, we'll start with a bit of physics, then at the end we'll do a little bit of maths. So I will show you the draft version of the 4th physics assignment, so you can understand what we're going to talk about today. Sorry that it hasn't been uploaded yet. It's just it takes quite a long time to prepare those. So I will upload them to the COMPOS webinars so you can have a look, and let's get started. So I'll share my screen as for everyone. I'll share my screen, and okay, so share. So you should be able to see my screen, and I will paste the pages. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the physics assignment 4. And it's very closely linked to integration. And it's not a coincidence, of course. Right, all is done. Okay. Okay, perfect. So let's have a look. So the first topic is the center of mass of a system. And there's a theorem of the motion of center of mass. The center of mass of a system moves like a material point whose mass is equal to the total mass of the system. And a consequence of that theorem is that if there are no external forces, the sum of the external forces is, if there are no external, or the sum of external forces is 0, the center of mass of a system moves in a straight line at constant velocity. So what does that mean? Well, if you have several objects, hello, Bait, and if you have several objects, you can you can treat it as a single object at the position of the center of mass. So, for example, if an artillery shell, which is traveling at a parabolic trajectory, so let's have a look at this. So you have an artillery shell which is following a parabolic trajectory like this. And it breaks down into several fragments, breaks into several pieces. So this piece can maybe traveling like this. Actually, I'll do this. This piece travels like this. This piece travels like this. And this piece travels like this. And this piece travels like this. But if you find the center of mass of those 4 pieces, the center of mass will continue traveling in a parabolic trajectory. That's quite an interesting consequence of that. But before that, we need to know how to find the center of mass. How to find the center of mass? Well, to find the center of mass, let's say we have the x-axis. We'll do in one dimension first. X-axis, and we have a mass m1 at position x1. We have mass m2 at position x2, and we have a third mass m3 with x-coordinate x3. Then the position of the center of mass can be found using the formula. X center of mass is equal to m1 times its coordinate plus m2 times its coordinate plus m3 times its coordinate all over the sum of masses, m1 plus m2 plus m3. So this is the formula to find the center of mass of three objects. Okay, so therefore, if you have multiple objects for n objects, you have the same formula, but n terms. But the formula can be simplified. Center of mass is equal to the sum of mi xi and I from 1 to n all over the sum of mi from I1 to n. How well do you understand how I got from this formula to this formula? Can on a scale of 0 to 10, please, in the chat. Okay, that's good. And of course, if you were paying attention in my previous webinar, if we have a solid object, if we, for example, let's say we have a cylinder. If we have a cylinder, we can cut this cylinder into infinitely many pieces. Infinitely many pieces. Of width delta x and mass, of width width delta x and mass m. And the formula m delta x, when you have infinitely many pieces, the sum of m becomes the integral of m dx divided by, well, the sum of m, which is just the mass of the cylinder. So that's an outline of what we can do. Sorry, I'll just refresh my screen because it's not working properly. Okay, but we go back to the first formula with three objects because we'll be using this for the first problem. So let's have a look. The first problem, we have three objects. Find the position of the center of mass. We have three objects in one straight line, 5 kilograms, 4 kilograms, and 1 kilogram. So I start I start this by drawing the x-axis and choosing the 0 position of the x-axis. Now, I can choose any position. So this is the x-axis. I can choose 0 where I like it. I can choose 0 to be here or here or here. But I'm going to choose this as my 0 position, as the origin. So this is 0. This is 2. And this is 5, of course. So this is x equals 0, x equals 2, and x equals 5. And then I just simply use the formula. So the formula for x center of mass is equal to m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So that is 5 times 0, because 5 is at position 0, plus m2, which is 4 times 2, plus 1 times 5, all over 5 plus 4 plus 1, 5 plus 4 plus 1. And that gives me, so that's 0, 8 plus 5, 13, over 5 plus 4 plus 1, that's 9, 13 over 9, which is approximately 1.44 meters. So the center of mass has a coordinate, so this is 2 meters, so it's approximately here. This is the center of mass. That means if I connect them with a rod and I place a pivot at this point, the system will be balanced here, because the center of mass of the system is here, so it won't tilt left or right. It is sort of, oh, it is. Of course it is. How did I get 9? 10, 1.3. 1.3 meters. So this is x equals 1.3 meters. I'm very sorry for those mistakes. Right. Okay. Oh, you have a younger brain. You have younger brains. You should be better at this. So the center of mass, and yeah, so that's that. The next bit, and this is concerning the movement of the center of mass. Two identical small masses, so M and M, are held 1 meter above the table. So they're held, connected by a compressed spring. So there's a spring here and a short string. So we cut the string and we release the masses at the same time. So the masses start moving in opposite direction. One moves down, one moves up, because they are accelerated by the spring. The lower mass hits the table 0.2 seconds later. Find the position of the second mass when this happens. So when the first mass hits the table, where is the second mass? Now, this, we could potentially write down a Suvat equation, but the problem is we don't know the acceleration of the first mass due to the spring. We don't know how long the spring is. So we have to use the theorem of the movement of the center of mass. So let's have a look. The theorem of the movement of the center of mass. The center of mass of a system moves like a material point whose mass is equal to the total mass of the system. The applied force is equal to the vector sum of all external forces acting on the system. So the only force, the only external force is gravity, is the weight, and that force is equal to 2mg. The external force is equal to 2mg. So what we do is we treat the object as a single object. And the only force acting is 2mg. 2mg. And the mass is 2m. So it's easy to see that the acceleration of this object is going to be g. For simplicity, I will take g is 10, and you can do this in any assignment. You can assume g is 10. 10 meters per second squared. In A levels, of course, you have to use 9.8 if you're doing maths, and 9.81 if you're doing physics. All right, so we considering the movement of the center of mass. Considering the movement of the center of mass. So we can use a suvat. S, we know that is 1 meter. Well, actually, no, it's not 1 meter, sorry. S, U, the initial velocity. The initial velocity is 0. The center of mass, we are releasing it. What happens inside the system doesn't really matter. We're not considering internal forces. We're only considering external forces. Initial velocity is 0 because we are just dropping it. V, we don't know, and we're not really interested in that. Acceleration is equal to 10, well, minus 10, technically, minus 10. And t is 0.2 seconds. Because what happened, we are interested in what happens in the first 0.2 seconds. All right, so we are not interested in v, so we take the formula without v. So that's s equals ut plus 1/2 at squared. At squared. Nope. At squared. And s is equal to. Actually, you know what? I'm going to use a different formula. I'm going to use y equals y0. The formula from one of the assignments. To find the position after 2 seconds. So y is equal to the initial position, which is 1 meter, plus 0t, because u is 0, plus 1/2 a, that's going to be 5. Okay, I'll just write 1/2 times 10 times 0.2 squared. And that gives me 0.8 meters. So the center of mass at the time when the bottom mass hits the ground, the center of mass is in the position 0.8. Because the center of mass falls freely under gravity. So center of mass falls freely under gravity. So by the time when the bottom mass hits the ground, the center of mass is at h equals 0.8 meters. So where is the second mass? Can somebody tell me? It should be intuitively easy to tell where the second mass is. Exactly. It has to be 1.6 meters. So the top mass has to be at h equals 1.6 meters. So a problem that seems very difficult at first, because we don't know the acceleration of the mass, the initial acceleration, because the acceleration is caused by the spring. And we don't know that force because we don't know the spring constant. We don't know how long the spring is. And we don't know so we basically know nothing. And yet we are able to answer this question just by considering the center of mass. Just one more thing. Why did I say that what allows me to say that the center of mass is at 1 meter? Because look, the mass is here, there's a spring, and say I'm not given the distance between the masses. What allows me just to use 1 meter? Several words in the text. Can somebody help me with that? There are a few words. They are of equal mass, but that's not the thing. How come I can say that it's at 1 meter? Short string, yes, that's important. Short string. When I say short, what does short mean? Short compared to what? The height, of course. The string is very short compared to this height. Therefore, they are approximately at the same height, of course. And small masses, the fact that they're small also tells us a lot. So actually, what we're dealing with is two very, very small masses. You can say that they're tiny. So in reality, we're treating the system like this. This is what we're doing. I've expanded that. Okay. So these words are very important: small masses and short string. So when you are reading a question, do consider those things because they play a big deal. Right. Okay, moving on. All right. Find the volume of a square pyramid of base 4 and height 7 by slicing it to thin square slabs. So this is a math question. This is an integration question, math. Okay, so what can we do? What can we do? Well, we have a square pyramid. Let's put it on, tilt it on to one side. Tilt it on one side. So we are looking at the pyramid from the side. I hope that makes sense. So we've turned the pyramid 90 degrees. And we need the axes, of course. We need the y-axis. Y-axis and we have the x-axis. So the height is 7. So the height of the pyramid is this. So that's 7. That's 0 to 7. And the base length is 4. So this is 2 and 2. So this is 2 and minus 2. And we're cutting it into cuboid slabs. Cuboid slabs. So what we're doing is we're cutting the pyramid like this. Into slices. We're slicing the pyramid. And each slice is a, well, you can call it a square-based prism or just a cuboid, like this. Okay. So to do this, we need, let's take a single slab. Let's take the middle one. I'm just going to paint it red. Middle slab. And it has a width of delta x, and the height of 2y, because this is y, this is x, and the width is delta x. And because we're taking the ith slab, so ith slab is going to be delta xi and 2yi. But obviously from here we can see that y depends on x, because it's a linear function. So let's write down, well, y is a straight line. It goes through 0, 0, and it goes through 7, 2. So it's quite easy to figure out that y is 2/7 of x. It's a straight line. That's the equation of the line. If you understand why y equals 2/7 x, please type 1. If not, type 0. Some interaction. Okay, good. That's fine. That's really good. And so the volume of this slab, because it's actually looks like this. So this is delta x, this is 2y. So the volume is going to be equal to 2y squared times delta x. Well, it's part of the pyramid, so it's delta v. Delta v I is 2i, the ith slab, the volume of the ith slab. And we're going to simplify this. Delta vi equals 2y. So it's going to be 4/7 x. 4/7 x squared delta x, xi, of course, delta xi. And delta vi is equal to 1649 xi squared delta xi. This is the volume of the ith slab, and if we need the total volume is the sum of those slabs. 1649 xi squared delta xi. I from 1 to n. But remember, the smaller the slabs, the closer we are to the true volume. The smaller the slabs, the closer we are to the real volume. So volume, the total. This is the sum 1 to n. So we can say volume is approximately that. The total volume of the pyramid is approximately equal to the total volume of the slabs. But we can also, as we make the slabs, so we use the Riemann sums. So the volume is strictly equal to the limit of delta x tends to 0 of the sum of I equals 1 to n of 1649 xi squared delta xi. So as delta x tends to 0, this sum becomes the integral from 0 to 7 of 16 over 49 x squared dx. Now delta x, as delta x tends to 0, becomes dx. So this is going from sums to integrals, and this integral is, well, it's a very basic integral. So you know how to do it. So you take 1649 out, 49, and you integrate x squared dx from 0 to 7. So it's going to be 16 over 49 square bracket x cubed over 3 from 0 to 7, and 16 over 49 multiplied by 7 cubed over 3, and 7 cubed cancels with 49. 16 times 7 is 112 over 3. Cool. So we found the volume. Let's try to find the volume of the old-fashioned way. Check. We know that, okay. No, I don't want to annotate. Okay, so moving on, I know that the volume, where would the limits go in the Riemann sum? The Riemann sum is you're taking all the slabs from the first slab to the nth slab. The first slab is at x equals 0. The nth slab is at 7. That's how these change from here to here. Does that make sense? From the first slab is at position x equals 0. You're summing slabs from the first slab to the nth slab, and here you go by x, by the coordinates of those slabs, from 0 to 7. These are the coordinates of the slabs. Here you can say, right, but we know the formula for the pyramid. We know the formula for the pyramid is 1/3. Okay, I'm not going to do that. the formula for the pyramid is 1/3. So the volume is 1/3 area of the base times the height. So it's 1/3. The area of the base is 4 times 4, 16. And the height is 7. And as you can see, it's also 112/3, which matches this one. Okay, not the easiest method to find the volume of a pyramid, but here you go. But the beautiful thing is it allows you to find areas and volumes of very complicated shapes by using Riemann sums and integration. Now, the next bit is find the position of the center of mass of the above pyramid. So it's not a coincidence that I've given you two very similar tasks here. So I'm just going to copy this. Now, the position here, the position of this slab is xi. And as you know, the center of mass is equal to m1 x1 plus m2 x2 plus etc. plus mn xn divided by m1 plus m2 plus etc. plus xn. So we need to work out the mass of this slab. And the mass is volume times density. So the mass of the ith slab, well, it's the volume of the slab, or of the ith slab, is the volume of the ith slab times the density. And the x position of the ith slab is, well, the yes, so we can place that here, so we can grab it from the previous one. So it's 16/49 multiplied by xi squared delta xi and times density. Well, I'll just put the density here. And mi xi, it's going to be the same expression, but with 1649 x cubed, xi cubed delta xi. Okay, so the x center of mass, the formula for x center of mass, becomes the sum of these, the sum of rho 16/49. Yeah, so mass is density times volume, just in case. You should be very comfortable with this, but just in case. 1649 xi cubed delta xi. Now this is approximate. I from the first slab to the nth slab, divided by the sum of rho 16/49 xi squared delta xi I equals 1 to n. And let's see. So this is the Riemann sum. And now we do x. So this is approximate x center of mass is equal to the limit as delta x tends to 0 of this thing. Which is equal to the integral from 0 to 7 in a similar fashion. Now, rho 1649 x cubed, there's no I, x cubed dx, and the integral from 0 to 7 rho 1649 x squared dx. And here this cancels out because they can be taken out, because these are constants, they can be taken out. So we are left with the integral x cubed dx divided by the integral of x squared dx. And of course, from 0 to 7, from 0 to 7. So it's going to be x to the power 4 over 4 divided by x to the power 3 over 3 between limits 0 and 7. Well, okay, technically I shouldn't do that. Technically I shouldn't do that. I should say this is from 0 to 7 and this is from 0 to 7. Okay. So it's going to be 7 to the power 4 over 4 divided by 7 to the power 3 over 3. So it's going to be 3/4 times, now 7 and 7 cubed cancel out, times 7, which is 5.25, if you like decimals, 5.25 meters, 5 meters, but just 7 is the height, so 3/4. So it's going to be 3/4 of the height. That's a kind of important consequence. So the center of mass of the pyramid is 3/4 of the way here. Or, yeah, somewhere here. So this is 3/4 of h, and this is 1/4 of h, quarter of h. And you can use this result for any square pyramid. It will all be the same. The center of mass of the square-based pyramid is 3/4 from the vertex, from the point. How well do you understand this solution on a scale of 0 to 10 again, please? That's impressive. Well done. The key thing is that you need to understand that You can find the center of mass of those slabs because you know the position and the mass. The mass is mi, the position is x. So that's how we do it. Okay. Now, one of the questions will be to do the same trick, but with a semicircular slab, semicircular block. So where is it? Semicircular. Yes. Problem 7. By cutting a uniform hemisphere of radius 1 into strips parallel to the flat surface, use Riemann sums to find the center of mass of the hemisphere. The density of the sphere is rho. Make a conjecture about the position of central mass of a hemisphere of radius r. So just like I did. First, I found 5.25. This is for this particular pyramid, and my conjecture is that for any pyramid, it's going to be 3/4 of the way. So going back to this, what we are going to have, we're going to have a hemisphere, and we're going to cut it into cylindrical slabs this time. Going to cut it into cylindrical slabs, and each slab has mass mi and the x position xi. So the x-axis can go like this, the y-axis can go like this, y, and you can use y is equal to square root of 1 minus x squared. In general, y is going to be square root of r squared minus x squared, but not important here. And the result will be this. I'm kind of giving you a hint. I'm giving you the answer here. The central mass of a hemisphere is 3r/8 away from the geometrical center. So what does that mean? So if you have a semicircular, hemisphere, the center of mass is here, and the distance is 3r/8. We're going to use this in the next question. Use this in the next question. Find the maximum mass that can be attached to the top of the light pole so that the system would not topple over on a flat surface. Basically, it is a question about stability. So let's have a look at stability. There are 3 types of stability. There's unstable equilibrium, stable equilibrium, and neutral equilibrium. So unstable equilibrium, if the object is displaced, it does not return to original position. So if you push this ball slightly to the right, it will not return to original position. In stable equilibrium, it will return. In neutral equilibrium, it will stay in the new position. So what does the fact that the equilibrium is stable mean? Well, let's take this system and tilt it. I'm just going to use a circle, and I'm going to tilt it. And let's have a look. So can I do this? That's better. I draw the floor. This is the floor. Now look what happens. The point of contact is here. This is the point of contact. And if we draw a vertical line from here, actually this here. If the center of mass is to the right of that point, so for example, if the center of mass is here, it will topple over to the right. If the center of mass is to the left of this point, so let's say the center of mass is here, it will return to the original position. Does that make sense? Please type 1 if it makes sense. That depending on where the center of mass is, it will either fall to the right or fall to the left. Brilliant. So basically, the critical position of the center of mass is here. So if the center of mass is here, this is going to be neutral equilibrium. The question is asking that, okay, imagine you have a hemisphere and a ball attached on a rod. Actually, I saw a video very recently. It was a very fun video. I think I'm gonna put it in the, I'm planning to add it to the, just give me a moment. Sorry. Okay, so this is a toy. It's very popular in Russia. So look what happens. If we tilt it, it returns to original position. Okay. Yeah. So basically, this is a similar system. It's a similar system, it's just a simplified version. It contains a hemisphere and a mass attached on a rod. Russian dolls. It's not exactly a Russian doll. Russian dolls are made of wood. This one is made of plastic, and it has a metal piece of metal inside. So if the center of mass is to the left, it will not topple over. You put it on the side and it goes back up. However, if the center of mass is here, it will topple over. And that's what we need to figure out. So we know the center of mass of the hemisphere is here. It's 3/8 of R. and r is 10 centimeters. So we know this distance. We know this distance. So we need to know what is the mass if the center of mass is here. Okay. So what I'm going to do is I'm going to take this system and draw it sideways. Okay, not very well, but what are you going to do? Okay, so, and I'm going to draw the x-axis. I'm going to draw the x-axis here. And I'm going to start the x-axis here at 0. You can start it anywhere you like, but I'm choosing this point. So this point is 20 centimeters. You can do it in centimeters, you can do it in meters. I'm going to choose centimeters, yeah, 20 centimeters. And we know that this position is 3/8 of r. So this is going to be 3/8 of 10, that's 30/8. So that's what? 30 divided by 8 is going to be 3.75, so minus 3.75 centimeters. This point. And this is 0 centimeters. The mass here is m. And the mass here is 3 kilograms, m capital. And we know that the center of mass, x center of mass, must be less than 0. X center of mass must be less than 0 in order for the toy to be balanced. Or if it is a toy, it doesn't really say. It's a system. So it's a hemisphere attached to a light pole, and you topple over. So which won't topple over. X center of mass. So we know that x center of mass, we know the formula is equal to m1 x1 plus m2 x2 divided by m1 plus m2. So that's going to be m1 is 3 kilograms multiplied by minus 3.75 plus m multiplied by 20 all over 3 plus m. And this has to be less than 0. Now, you have a fraction which is less than 0, but this thing is positive. It's a mass. So the fraction is only negative when the top is negative. So I can multiply both sides by 3 plus m because it's positive. So it's going to be minus 3 times 3.75 plus 20m has to be less than 0. So 20m must be less than 3.3 times 3.75 is 11.25. 11.25. So m must be less than 11.25 over 20, which is over 20. That is 0. Okay, 0.56 kilograms. 0.5625 kilograms. So the maximum mass that can be attached is 0.56 0.5625 kilograms in order for the toy to be stable. Is that making sense? And maybe any questions? You can tip the hemisphere up to 90 degrees, sometimes even more. Oh, because then, okay, there's a, you can say it will not topple over. Like, I mean, if it's 0, it will be in neutral equilibrium. So you put it on the side and it stays on the side. You kind of want it to go back. Okay, the way the question is asked, I think you can use less than or equal to. Yeah, if it's 0, it would just lie on the side, but you want it to go back. So, I mean, I say won't topple over, so technically, I mean, if you're being strict, then yes, it's going to be less than or equal to. So, if m is equal to 0.5625 kilograms and neutral equilibrium. Neutral equilibrium. The toy that you saw in the video can be tilted more than 90 degrees. It can, as long as it's a sphere, because with a hemisphere, you reach a point where it's on the edge, and it's a whole different scenario. It's a whole different scenario. So you need to consider the shape of the base, because it would tip over the edge. If you topple it over, let's say, more than 90 degrees, it would look like this. And let's say the center of mass is here. It would still topple over because the point of contact is here. The point of contact is here. And you are to the right of that contact point. So it would topple over. But if the shape is like this, for example, then you can tilt it. Yeah, the center of mass is here. The point of contact is here. Even if you turn it more than, if you tilt it more than 90 degrees, it will still return to the original position. Okay, moving on. Problem 16. This is a math question. Maths question. Maths question. Sine to the power 17x times cosine x dx. How do I delete that? Somebody. Okay, so you have this integral. Well, you can't integrate it directly because it's not an integral from the table. So you have to use a method. We know two methods of integration, by parts and by substitution. You could try doing it by parts, but you won't be successful. And you have to learn it the hard way. There's no shortcut to integration. You just have to gain experience. Integration is an art, is an absolute form of art. Here, because you can notice that cosine is the derivative of sine, it is a substitution. And of course, there are multiple rules of integration, but it all comes down to experience with integration. And really good mathematicians. So basically, what makes a good mathematician is the ability to integrate. So here, the substitution is, you have two options, either sine x or cosine x. Now, imagine you said, okay, I'm going to substitute cos x. But then you can't really describe this in simple terms of u. So it makes more sense to make the substitution sine x. Substitution, and u equals sine x. And then the next stage, you find du over dx. Du on dx is equal to the derivative of sine x, which is cosine x. Cosine x. And you can multiply both sides by dx. You get du equals cos x dx. And would you look at that? This thing is this thing. And this thing is u to the power 17. So this is u17, and this is du. And voila, the horrendous integral becomes something incredibly simple. So after substitution, this becomes the integral of u to the power 17 du, which is easy to find, which is u to the power 18 divided by 18 plus c, which is, and you do reverse substitution. So you go 1 over 18 sine to the power 18 x plus c. And that's it. This integral, which initially looked very difficult, is actually just this. As a general rule, you can remember that if you have sine to some power x cos x, then the substitution is sine x. If it's vice versa, then it's cosine x. So whichever one is not to the power of 1. So in this case, substitution u sine x. And if you have an integral in the form this, cosine to the power nx, then the substitution is u to the is called cos x. So the hardest thing about substitution is to figure out what the substitution is. There are several rules, and just keep doing it until you get it right. Sometimes you do trial and error. You try one method, it doesn't work. We try another one. Okay, works. And two more integrals. They look incredibly similar. Sine cubed x and sine to the power 4x. But the thing is, the methods are completely different. And these are cases. If you have a cosine x to the power n, and you have cosine x to the power n, you have an odd power and an even power. So if you have an odd power, you use substitution. Odd power. Odd power. You need substitution. Substitution. And if you have an even power, you need to use identities. Even power, trig identities. Well, no, you need a specific trig identities. Even power, you need power reduction formula. Power reduction. There are two power reduction formulas. You know them. You might not know that they're called power reduction formulas. So basically, you reduce the powers until you get an odd one. So for example, if you start with sine to the power 6, you reduce the power to sine cubed, and then you can use substitution. In case of 4, well, you can't, because 4 will never become odd. Okay, so what is the substitution? The substitution is opposite to what you have. So if it's sine cubed, the substitution is cosine x. You'll see why. Well, let's see, du dx is sine x. And of course, that means that when we multiply both sides by dx, we get du equals sine x dx. Okay, so what happens here is we write it down as the integral of sine squared x sine x dx. But the substitution is cosine x. But we know that sine squared x is 1 minus cos squared x. So we write 1 minus the integral 1 minus cos squared x sine x dx. And we know that sine x dx is actually du. So we get 1 minus u squared du. And now it breaks down into two very simple integrals. One du. Sorry, of course, I made a mistake here. This is minus sine x, so it's minus sine x dx. So minus du is equal to sine x dx. So this becomes minus du. So this is going to be u squared minus 1 du. And it breaks down into two integrals of u squared du minus the integral of 1 du equals. All right, so the integral of u squared is u cubed over 3 minus u plus c. Now we do reverse substitution, so it's going to be 1/3 cosine cubed x minus cosine x plus c. One-third cosine cubed x minus cosine x plus c. A quick vote. How well do you understand this problem? Any questions? Abate, brilliant. All right, brilliant. Very good to hear. And problem 8. Now here we won't be able to do the same thing. It's not possible here because sine cubed x, we have used triggered into if you wanted for that one. For this one, well, we could express it in terms of was tan cubed x. These only works with sine and cosine. The integral of tan, it might be sec. I can't, off the top of my head, I can't see it. I can't see it happening. Tan. What's that? Sine 3x. Yeah, you can use this formula. You can use this formula, but this is for sine 3x, not sine 4x. You could have done this. Yes, absolutely. It would give you the same result. But so for here, we need to use the power reduction. There are two power reduction formulas. So sine squared x is equal to 1/2 minus 1/2 cos 2x, and cos squared x equals 1/2 plus 1/2 cos 2x. These are called power reduction formulas. And so this is what we're going to do. And we're going to simply work with sine 4x. We're going to work with the integrand. Sine to the power 4x is equal to bracket 1/2 minus 1/2 cos 2x squared, and this is a quarter, minus double, so it's a half, double the product, half cos 2x, plus the square of the second number is a quarter cos squared 2x. Okay, holding that thought, we write down separately what is cos squared 2x. Cos squared 2x. So we use the power reduction formula again. So it's going to be a half plus a half cos 4x. So we plug that in. So it's going to be equal to a quarter minus a half cos 2x plus a quarter times that, so it's 1/8 plus 1/8 cos 4x. Okay, and finally we combine the terms without cosine. It's going to be 3/8. So a quarter plus a 1/8 is 3/8 minus a half cos 2x plus 1/8 cos 4x. I hope I didn't make a mistake here. Okay. And then I simply take this and find the integral. Equals, actually, you know what? I'm just gonna do it here. The integral of sine to the power 4x dx x dx equal to the integral of that dx. Okay, so that's going to be 3/8 x 3/8 x minus. Now the integral of 1/2 of cosine 2x is going to be a quarter. The integral of cosine is sine, a quarter sine 2x plus 1/8 cos 4x. So the integral of that is going to be 1/32 sine 4x and plus c. Any questions here? Does everyone understand how I got from here to here? Like how I got that? I'm using the fact that the integral of sine ax plus b dx is, so the integral of cosine ax plus b is equal to 1/a sine ax plus b plus c. Okay, so I'm using this fact here. So that's why 1/2 becomes a quarter and 1/8 becomes 1/32. Yeah, that's a super useful formula. I mean, I mean, look, honestly, I don't remember that. My head is too busy with other stuff. So what if I need it? There are formulas that I do remember, and I just write down cosine 2x is equal to 1 minus 2 sine squared x, and I get sine squared x is equal to a half minus a half cos 2x. So earlier this evening, I did exactly that because I don't remember this. I can't honestly remember all the trigonometric formulas. So if I need them, I just get them. In a similar fashion, you get cosine 2x equals 2 cos squared x minus 1. From here, you get the second reduction formula, which is cosine squared x equals a half plus a half cos 2x. So two things, either you remember them or you know how to get them very quickly. Okay. So the stuff that I can't get very quickly, I remember. The stuff that I don't need to remember, I don't. Limited capacity, of course. Okay, yes, thank you for coming. And the recording will be available in a couple of hours. It takes a couple of hours to process. And good luck in physics assignment 4. Do have a look. You can already start assignment 4. The problems won't change. There will be probably one more problem. The link is here. You probably all have the link, but just in case, you can have a look at the assignment and start working on it. We will add some. There will be some theory added, perhaps. Might contain mistakes. I haven't proofread it. Haven't proofreading it yet, but that's pretty much what it's going to be. Yes, you can print the board. I think you just need to save it as PDF, and then you can print it. I've never done this, but people say you can do it. Right. I'll see you next Tuesday. Yes, we're back Tuesdays. It's just yesterday I was busy, but I'll see you next Tuesday. Well done.